The broadcast is now starting. All attendees are in listen-only mode.
Ladies and gentlemen, welcome to today's AIC seminar on innovations in food safety for food producers and manufacturers. And today I have my guest speaker, Professor Paul Gadek from James Cook University. First off, I'd like to thank our sponsors. Department of Science, IT and Innovation sponsor this webinar series, and it is delivered by the Australian Institute for Commercialisation. Now, a little bit about the AIC. We're a not-for-profit organisation, and we're here to help industry, research organisations and government departments work together to bring innovative ideas to market. And we deliver a range of services and workshops and the Queensland Inventor Service and also these webinars. Now, the objectives today is to hear about the work of the Rapid Assessment Unit, which is a collaboration between James Cook University and the Department of Agriculture and Fisheries, and to hear about the latest scientific advances in the non-destructive testing of produce. Now, let's start talking briefly about what we mean by collaboration, since the Rapid Assessment Unit is a collaboration. Collaboration is about organisations communicating and working together, building on each other's ideas to do something new or do something differently and creating value. Now, there's a lot of talk about collaboration, and that's why this seminar is a particularly good example of a successful collaboration. Now, we're going to talk about the Rapid Assessment Unit today, but I'm going to start off, since today's talk is about food safety. As everybody's aware, there's been a lot of things in the news lately about food scares from imported food. There was a scare about hepatitis A in the berries, and there was also one about canned food safety from canned tuna coming from Thailand. Both of these scares were very serious scares earlier this year. So consumers are looking to buy more Australian grown food these days, and also the government is looking at possible changes to the food labelling laws. So there are opportunities for Australian growers and producers to actually market their produce. But how can our growers demonstrate that their produce is safe and of good quality? So that's where the Rapid Assessment Unit helps this process. So Professor Paul Gadek is involved with the Rapid Assessment Unit, and as I said, this is a really good example of a collaboration between a research organisation and industry. I'd like to hand over to Paul now, and he'll talk to you about the Rapid Assessment Unit in more detail. So Paul, how did the collaboration between James Cook University and DAF that created the Rapid Assessment Unit originally come about?
Thank you, Sam. Again, I need to go back into history. The Rapid Assessment Unit has been in existence since 2003 or 4, I think it is. The way it came about is that in 2002 there was an approach by an industry partner, who is now one of our industry partners, to evaluate a grading system that he was distributing and was the agent for in Australia. So in 2002 he commenced discussions with the Department of Primary Industry and the horticulture industry to evaluate his system. And I got to hear about it because some of the discussions that were occurring were between staff of DPI that were based here in Cairns, but also some of the agricultural producers up on the tablelands to the west of Cairns here. And there was some excitement about it. So in February 2003, the next step for us was to develop a non-disclosure statement, which we had to get each of the entities to sign. So Department of Primary Industries and Fisheries at that stage, the industry partner, Brettech, the industry or the other industry partners that were involved in producing the various parts of the equipment, and James Cook University all signed a non-disclosure statement which enabled us to start sharing information between the parties And so we could start to develop future collaborations, or what that future collaboration might look like. In May 200 and, sorry, that was my phone going off, of course. In May 2003, the DPI then secured some funding to progress this joint collaboration with JCU, particularly in the area of non-invasive technologies. And then in February 2004, JCU and DPI officially signed a collaborative agreement, a joint venture, to establish the Rapid Assessment Unit on the Cairns campus here. We also had to develop an MOU between the Department of Primary Industries and James Cook University, so that this formation could be initiated under the terms of that official MOU. And that MOU was subsequently launched by the Minister for DPI at the time in May 2004. So the next steps then in forming the Rapid Assessment Unit were to develop a, I guess if you like, the terms of engagement. And what we did then was to sit down and produce a business plan of sorts, which contained a detailed plan of the technology, what the work was that we wanted to, what sort of human resources and skills and expertise we need to develop, our main strategic initiatives and outcomes, our objectives, both short and long term, what our milestones and performance indicators were going to be, the structure itself, we had to make sure that we had those core agreements developed, and we had a number of subsequent agreements that we developed. We needed to make sure, of course, that we had the appropriate infrastructure to enable us to proceed with the collaboration. We had governance structures that we needed to put in place, intellectual property that we needed to manage, and marketing and communications that we also needed to develop processes for. And so we developed, and of course there was a deal of financial information. How exactly was the projects and the funding going to be handled? You know, who was going to be responsible for submitting project applications or consultancies? How was that any funds that were received going to be handled, and who owned what in terms of the operations of the Rapid Assessment Unit? And so we needed to develop background IP before we came together, joint project IP, a register of IP, and various, you know, financial structures and understandings as well. So that was basically the way that the collaboration developed. The Rapid Assessment Unit is still ongoing today, so it's been quite a, in terms of its longevity, quite a successful initiative, and in terms of our output, in terms of satisfying both the requirements, I suppose, of the university, who are not, who do not necessarily want to commercialise research, but want to undertake research, and you know, their core business is teaching and research, and DPI, who needed, or who wanted to be able to undertake research in a manner that was not available to them at the time, and to be able to leverage funds that the university researchers had available to them that weren't available through DPI. So that's the main steps that created the Rapid Assessment Unit, Sam.
Thanks, Paul. That's very interesting, and that links very nicely to the seminar that we ran earlier this week, where we're talking about what it takes to collaborate between a business and a university and the government. So what you're saying is it came about firstly through the sharing of confidential information and a market need, and then you moved on to develop a formal agreement, and from there a business plan. So that's interesting to hear about how the step through the process, and of course it took a bit of time. But let's move on to the future, to what's occurring now. What sort of testing is the unit currently carrying out?
Thanks, Sam. Yeah, so what we were set up to do, I suppose, was to assess and improve the safety and quality of food, agricultural products, through the development and implementation of non-invasive technologies, and to assist in the commercialisation of those activities or those technologies through our business partners. And I have to say at the start that it's a project-by-project funding operation as well. So each of the projects that we develop that obtain funding are almost like separate entities that exist within the Rapid Assessment Unit. But what do we do? What does non-invasive technologies actually mean? Well, when we set up the RAU, our initial focus was on the application of near-infrared spectroscopy to assess the internal and external quality attributes of produce, particularly in inline situations, and we wanted to then advance the application of NIR spectroscopy as an alternative to some of the existing very expensive and time-consuming traditional analytical methods. There's a little bit more about the work that we do on that web page, which I think is on your screens at the moment, which you can access if you go to the JCU website, James Cook University website, and search under one word, rapid assessment, just rapid assessment as one word. You will come to the link to the web pages that you can see on the screen before you, and that gives you a little bit of the background, some of the technology that we do, our current research and publications as well, so that you can see the sorts of things that we do. But as I said, what we're interested in is this non-invasive, the application of these non-invasive technologies. Non-invasive technologies are those that don't spoil or invade or in other ways destroy the product that we're looking at. So we wanted to be able to assess internal attributes of food very rapidly in inline situations that doesn't destroy the product itself. So things like near-infrared spectroscopy allows us to do that because light at this particular set of wavelengths can actually penetrate into the fruit internally to a certain distance, and the way then it interacts with chemicals or the chemistry of the product itself allows us to determine the particular attributes of that product. There are other non-invasive technologies which we're also interested in, and we've started to move into some other areas, but things like X-rays and there's a range of other non-invasive technologies which we might look at in the future. But at the moment we're primarily concentrating on NIR. So that's a sort of brief overview of the sorts of things that we do. I would encourage you to go to that website because it, I think, would probably explain things more eloquently than I have. But there we are. Sam, I don't know if you want me to go into more detail about NIR spectroscopy and how it works itself. It might be of benefit to understand what it is that we actually do with the NIR.
Yep, I think that would be useful to give a brief overview for the audience, since there's probably some food producers listening in. If you could just rapidly cover that off, that would be good.
Yes, nothing is simple in this world, is it? Nothing is simple. So, as I was explaining, we've got produce, which is basically organic matter, which is composed of molecules, and if you irradiate those molecules, they and radiated by an energy source such as NIR light, they'll change their vibrations from one energy level to another, and we can pick these transitions up, and so what we then do is to look to see how we can calibrate, as we say, between the change in the energy levels that we're picking up and the particular chemical component that we want to analyse. So the process that we go through, I won't go into that in much more detail because it's quite theoretical. But the basic NIR calibration process that we use, first of all, we need to, of course, have a sample, and we need to have a property of interest. We need to determine what that property is that we're going to be looking at. And then we need to determine how we're going to present that sample for NIR analysis. We then undertake the measurement of that sample using NIR. In other words, we collect spectra of the sample. And then we need to analyse against a reference. So NIR is a secondary method and it requires calibration. So what we need to do is to then undertake laboratory testing to look to generating a reference library of the chemical that we're interested in detecting in the produce. And it's the quality of this referencing that will dictate how successful we're going to be with the calibration model. So the next stage then is to develop what we call a calibration equation between the NIR spectra that we've collected and the chemical loadings. And we do that mathematically. And then what happens is that we then can validate that calibration equation to see if it accurately predicts the property of interest. So the more robust and accurate the calibration equation is, the more confidence you have that the NIR spectra is picking up the particular chemical attribute of interest. And then we can go on and apply that now, because we know we've got a very robust calibration equation that's going to pick up internal attributes of the fruit, of the produce. We can then predict with a new set of produce what its chemical components are going to be in terms of the library that we've just produced. So it provides us with a future predictive model of the particular chemical component of interest. So, I mean, this NIR's sort of been used for decades as a diagnostic tool. It's not, NIR itself is not something new, but developing those libraries, developing the ability to pick up that calibration equation that's robust for the particular component that you're interested in is where we come in. It's where we come in. Once we're able to do that, NIR offers a very rapid and a very repeatable and a very cost-effective method of predicting properties of interest. Those properties of interest could be things like the moisture content in wheat, which has a long history. Could be looking at the oil content in sandalwood, for instance, which was looked at a few years ago. Could be ripeness or quality of fruit, or it could be nutritional requirements of individual plants. And we could predict what they might need without destroying the product itself. So that's the real key to this. It relies on developing a collaboration equation that relates the property of interest to the NIR spectra. So that's what we do.
Thanks for that. That's quite technical, but I think we can understand and follow that. So the key question then is, who benefits the most from this service? Who are the sort of people who use this service and have benefited from the establishment of the Rapid Assessment Unit over time?
Well, I mean, obviously we benefit, the university benefits, the Department of Primary Industry benefits, and our industry partners benefit. I mean, what we're trying to do is to ensure that that technology is commercialised and is available, and then the savings that the producers are able to gain are then transferred to consumers. Not only the savings that might be gained and passed on to consumers, but also the confidence that what it is that the food is supposed to, or the produce is supposed to contain, is accurate and is predictable and is you can bank on it. And so that's a very important thing. I think that's a very important thing in terms of being able to value add to your food product. Sam's just put on a picture from the website where there we've got an image capture of an avocado which has a scar on it, a scar defect, and we've just got some pictures there that are looking at detecting that scar under the skin, and so we can actually detect that as the avocado moves through in an online setting on a conveyor belt very, very rapidly, and exclude that particular piece of fruit as it passes, and it won't go to the consumer. But you could, for instance, look at oil content of the avocado. You could look at its days to ripeness. So if you could imagine that when you go to a supermarket and the label on the avocado says this avocado will be ripe in 3 days, and you can say that with some confidence, there's a value to the consumer in being able to purchase that avocado. So we can do that with a range of produce and product, and we're able to then predict certain attributes of those product, sugar content, for instance, or whatever it might be.
Very interesting, thank you. So there's benefits for the producer as well as potentially for the consumer down the road. So has there been any other really interesting things that have been learned as a result of the unit's work?
Well, yes, the nature of research is that you always develop interesting things, and again, I refer to the website. You'll see a range of publications and outputs that detail some of the work that we've been done. On the screen at the moment you can see a visit to the Rapid Assessment Unit by delegates at an avocado growers conference that we had then. You know, so we have this ability to be able to showcase the technology as well to industry delegates. You can see in the foreground there, this is part of the sorting conveyor belt system that one of our industry partners, Brett Tech, is involved with at the moment, and the actual business end is behind the Queensland Government logo there, so you can't see much about where the NIR stuff is happening, but that's the conveyor belt there. Look, in terms of research, because that's what the university is very keen to do, there's been a number of things that have come out of this and the application of NIR to produce that have been quite surprising. We had a PhD student who used NIR spectroscopy on ants to identify the colony in the nest of origin. In a sense, he was using NIR as a substitute to genotyping of the ants, which is absolutely fascinating. We've had work done on plant defences in trees to determine the feeding ranges of various animals in the rainforest. We've had work done on recognition cues for insects, using how NIR interacts with the outside of the insect. We've had work done on soils and so forth. One of the more recent work by a PhD student is now on your screen at the moment. This is by Cassandra Rigby, who's a PhD student at James Cook University. And she's been working on a further application of some of the work we did, or I shouldn't say we, I should say Brett Wedding and Steve Graff did with the Rapid Assessment Unit last year. And that is on how we go about aging fish. So here you see just the journal screen print, where she's been using NIR to age deep water sharks. Now, you might ask yourself, well, why is this useful or important? Well, those of you in the fisheries industry would know that the way that fish populations are aged is by basically killing the fish. So you collect your samples of fish, you kill them, you then extract what's called an otolith, which is a structure in the ear of the fish, and you can see that on the right-hand picture there. The otolith continues to grow while the fish is alive. So all the time the fish is alive, the otolith continues to grow, and there's material laid down on that otolith in rings. And so what scientists can do, what they do at the moment, is then after they've extracted the otolith, they then section the otolith, very fine sections, and then they visually count the number of rings on the otolith to determine how old that fish was when it was killed. Unfortunately, counting those rings, so sectioning, developing the sections, the fine sections, and counting them is very labour intensive, but it also takes a hell of a long time, many months. And so by the time you get a picture of the population age of the particular catch which you caught, 12 months ago, it's a bit late to sort of then apply it and say, oh gee, I think these fish were a bit young or whatever. We should have left them in there for a little bit longer. So there's value in knowing what the age of a fish population is to manage and harvest at appropriate times. What we can do with the NIR, we can now, we've now done this with initially with the bony fish, but we can accurately determine, in other words, we have a robust correlation between the chemical components in the otoliths and our calibration equation, which is very robust in terms of the traditional methods of aging fish by looking at their otoliths. So we can correlate those very well, but we do it almost instantly. So as soon as that otolith is out and dried, we can determine how old that fish is. What we're doing is not picking up the rings. What we're doing when we look at the NIR scan and that calibration equation of those otoliths is actually picking up chemical components. We're picking up chemical components in the otoliths that are unknown at this stage. From there, and our next stage in this work is then going to look at how we can rapidly and without killing the fish pick up those chemical components in other tissues of the fish, like the spines, for instance. So we might be able to sample one of the spines and instantly age the particular fish without killing it. What Cassie has done is now take that a little bit of a step further and show that she can age sharks, which are basically non-bony fish. They have a cartilage system. And she's been able to pick up the same sort of chemical signal using NIR, which can then go on to determine in real time the age of whether it's a bony fish or a shark. So that's particularly exciting in terms of the way we might be able to manage our fisheries resources into the future. So that's something that's just come out.
Thank you. That's very interesting. So following on from that theme, how do you think things will change in food safety testing over the next 5 to 10 years based on the sorts of work that the unit has done recently?
Look, I think it's what's happening is in the industry, in the NIR industry, if you like, is that the technologies are shrinking. They're becoming handheld units, for instance. We're looking at handheld units that you can take into the field, so very low cost in-field monitoring. We can actually now produce small NIR units that are specifically calibrated to a particular component, and so you're going to see those sorts of things developing in the new year in many agricultural and food sectors. So things like you might be able to use them for plant breeding applications. You might be able to use them for individual plant monitoring to ascertain nutrient requirements on an individual basis, and in fact we've got some work proposed on that very scheme at the moment, which would then allow you to limit the amount of fertiliser that's broadcast. If you could actually determine, for instance, what individual plant needs are in real time, you then don't need to over-fertilise or under-fertilise to produce your particular product. So, and just things like in seafood, again, you might be able to, or you can in fact, determine whether there's a particular chemical component in the fish fillet that might reduce its palatability to human consumption. It might pick up, for instance, things like cigatura. And so you've got a combination of these sort of individual research applications in aquaculture and fisheries management, but also have they also link to environmental management tools. So you can start to obtain very reliable and very rapid analytical information that will allow you to achieve more environmentally friendly and sustainable practice. So I think those things are going to go on, and as I said, our future work is also going to involve other non-invasive technologies such as nuclear magnetic resonance, for instance. Acoustics is something we're using on mud crabs at the moment. X-rays, bioelectrical impedance, ultrasound, those sorts of things have different applications to different products, if you like. And so we're looking at those to see how those might be applicable for research in the future.
Well, thank you very much for that, Paul. Well, we don't have any particular questions coming up at the moment, so I might just summarise up and say how interesting it is to have had a discussion about how it came about and what's happening in the future. And I would like to thank you very much for your time, and thank you, ladies and gentlemen. I'll bring the seminar to a close, and for those who are interested, there will be the link available on the QMI Solutions YouTube site. Thank you very much for today. Goodbye.